All right, so these observations give us a very useful way of looking at things. Here you have an example of what will happen over time in a closed system. You see here, time is on this axis along here, going from left to right, and what you're seeing here is that every time energy is transformed in the system, the entropy, the gray stuff, increases, and the Gibbs free energy, the blue stuff, goes down. And again, that's a statement of the second law of thermodynamics. The second law really states that it can't go up. But in reality, it always goes down every time the system changes state. So this then gives us a relationship among these three concepts. The first concept being the free energy, the second concept being the entropy, and together the entropy and the free energy make up the total energy, or the enthalpy of the system. So that means this, that the enthalpy is equal to the Gibbs free energy plus the entropy, at least in the way that I'm defining entropy here. But remember, the physicists define entropy as this concept of entropy times the temperature of the system. All right, so if we look at this system, we can actually then solve that equation, that H equals G plus S, for the Gibbs free energy, and that gives us a very useful way of looking at biochemical reactions. So if we look at this here, again, since the enthalpy is equal to the Gibbs free energy plus this entropy, now here I'm expressing entropy in the way the physicists do, the temperature times the entropy, then we can solve the equation for G, which would give us G equals H minus this entropy. Now, the thing about that is for any given system, it's a very, very difficult thing in practical terms to actually measure all of these things, the enthalpy and the free energy and so on. In general, however, measuring the change in energy is not that difficult. And so this is typically how we express the equation. We use the delta. If you remember, delta means change. So delta G is the change in the Gibbs free energy, the usable energy in the system. And so therefore, that's equal to whatever change in the enthalpy is. Now remember, if the system is closed, the first law says that has to be 0. And then the temperature is going to be here, because again, I'm expressing now entropy in terms of the way the physicists do. This temperature has to be in absolute temperature. So we're going to have that in kelvins, not in Celsius or Fahrenheit. And then the delta S, this is the change in the physicist's concept of entropy, which is the proper way of actually expressing it. So this is the central equation for all of metabolism. The change in the Gibbs free energy is equal to the change in enthalpy minus the entropy. Now, if you look at this as a closed system, remember the closed system says that delta H has to be 0, that the total amount of energy in the system, not free energy, but energy in the system, must be constant. Therefore, the change in H must be 0. Now, if that's true, then look at this. Whenever delta G goes in one direction up, delta S has to go in the opposite direction in order to keep the equation the same. All right, so that then gives us, like I said, the central equation for all metabolism. But what does it mean, and how can we get an intuitive sense for it? Well, that's what we need to get, because this is how we're going to express all of our concepts of metabolism from now on. Whenever we look at any reaction in which this delta G, just as I showed you in the previous slide, is less than 0, whenever that goes down, then we have a reaction that we call spontaneous. And what do we mean by spontaneous is this, is that if something occurs on its own without being pushed, without having any kind of a force applied to it, well, not necessarily a force applied to it, but if it just happens on its own, then it is spontaneous. So for example, if I hold a rock up here and I release it, the rock will drop and go down. It won't go up. All right, here's another example. Let's take a ball and put it on a hill. Now the system is just the ball on the hill. There's no wind and there's nothing else. We're getting rid of all that other stuff. We can show that the total free energy in the system is proportional to the height of the ball above the bottom of the hill. So when I start with the ball up here on the hill, then I can release it and it won't roll up the hill. We know that. It'll roll down the hill. That's what I mean by spontaneous. It spontaneously goes down on its own. We don't have to push it. Gravity's just taking it on its own. So that type of reaction has a delta G that is negative, is less than 0, okay, if we were to calculate it. Again, if we calculate it, here's how we would do it. Like I said, the free energy is proportional to the height of the ball from the bottom of the hill. The way you calculate delta G is the free energy at the end of the reaction minus the free energy at the beginning of the reaction. That's how it's calculated. So if we have this, the free energy when the ball is at the bottom of the hill is less than the free energy of the ball at the top. Something less than something subtracting away from it. In other words, we take something with say 0 free energy and we subtract something positive from it, then we get a negative number, and that means that the delta G is less than 0. That reaction is also defined as exergonic. It's releasing free energy. Exergonic meaning it is a reaction in which the energy is being released out into the environment, or within itself, it's just being released. Now, you might be looking at this and saying, wait a minute, that's different than what I learned in chemistry. In chemistry, I learned that these kind of reactions are exothermic. I'm not debating that, and I'm not actually contradicting that. We're not saying different things. Exothermic is a special type of exergonic. Thermo means heat. Exothermic reaction means it releases heat. There are other reactions which can be exergonic, but they don't release heat. They could release light, like, for example, an atomic bomb. An atomic bomb goes off, yes, it releases light, and it releases heat, and it releases a big whopping bang. All of those things are the forms of energy that's being released by the bomb. That's all exergonic. Only the heat part is the exothermic part. So this reaction, then, this concept of exergonic means releasing energy of any sort, light, heat, sound, whatever. So this reaction then is exergonic, has a delta G that's negative, and it's spontaneous. I want you to equate those three concepts. They all mean the same thing. When I say a reaction is spontaneous, I instantly want you to think the delta G is negative and it's exergonic. If I say the reaction is exergonic, I want you to instantly think it's spontaneous and the delta G is negative. Those three things mean exactly the same thing, and I want you to completely equate those. So practice with that. Make sure you see that. And we're going to see that a lot coming up in the next parts of this lecture and the following lectures. Okay, so what does that mean, though? This is not a metabolic system, right? Balls on hills are not metabolic systems. Well, metabolic systems are chemical. We're a biochemical reactor. So if we look on this axis here, on this picture, this is measuring the free energy of some chemicals in your body. Say, for example, we're looking at glucose. The total amount of energy in the glucose is here. We actually have to add water to it as well. I'll talk about that later. But that would be the free energy of the glucose. And what you're going to do in your metabolism is take that glucose and break it down. Break it down to, say, carbon dioxide and water. When you do that, the free energy of the products, of the carbon dioxide and water, is down here. Okay, so now we measure free energy the same way we always do. The free energy of the system at the end of the reaction minus the free energy of the system at the beginning. Well, this is a smaller number at the end than it is at the beginning. Therefore, this free energy minus this is going to be a negative number. So therefore, the delta G is negative. Like I said, it's therefore spontaneous, which means sugar will break down into carbon dioxide and water spontaneously, just like a ball rolled down a hill spontaneously. That means also it's exergonic. It's releasing energy of some sort. Okay, and the amount of energy that's released is this, is the difference in what the free energy is at the end minus the free energy at the beginning. Okay, so those are spontaneous reactions, and those reactions are the kinds of reactions that you use to release energy from your food, for example. Now, compare that to a ball at the bottom of the hill going up the hill. Same kind of idea. In this case now, if we put the ball at the bottom of the hill, we don't expect it to just go on its own and roll back up the hill. That's because the reaction is not spontaneous. It doesn't happen on its own in this universe. If it does happen, that means there has to be something else pushing it, some other object pushing this reaction up the hill or pushing this ball up the hill. It could be the wind, could be a kid kicking it, whatever. But in that case then, since the reaction is not spontaneous, the delta G must be positive. And again, remember, delta G is the free energy at the end of the reaction minus free energy at the beginning. Well, now this number is bigger than this, so I take a bigger number, subtract a smaller number from it, that's positive. So whenever we have a delta G greater than 0, that is a non-spontaneous reaction. And the free energy goes up. And we refer to that as endergonic, meaning it's absorbing energy, which is getting at what I just talked about before. When the ball goes up the hill, if you see a ball going up the hill, whether or not you can see why it's going up the hill, you know there must be some other part of the system pushing it up the hill, which means there's some other part of the system that is giving the system energy to change its state in a non-spontaneous way. Okay, so this is pushing itself up the hill, or something is pushing it up the hill. It doesn't push itself. So same thing as before. Endergonic means delta G greater than 0 means not spontaneous. All right, now that in your body then, that would be a reaction like this. Take a bunch of amino acids and construct those amino acids into a protein. The total amount of free energy in the system when you just have a bunch of amino acids is much lower than the free energy of the system when all those amino acids are connected together into a protein. Which means this: take a bunch of amino acids, put them into a jar, shake them up, and no amount of shaking is going to make them go into a protein. There has to be some other energy source that pushes it to make the protein, because the delta G is positive and it's not a spontaneous reaction. So amino acids will not spontaneously form into a protein any more than a ball will spontaneously roll up a hill, or your pen is spontaneously going to jump off the desk and into your hand. There has to be some other energy source to do that. And that's exactly why you eat. We're going to get into that here very shortly. Example that comes right out of your metabolism. This is one of the most important reactions that occurs in your body. And we'll talk about why here very shortly. But what you're looking at here is adenosine. And we've seen this before. This is adenosine. Remember, this has got the sugar on it. It's got the base coming off of it, adenine. This is a ribose sugar. And then it has a phosphate group on it. That's what makes it adenosine. But this particular form of adenosine is the triphosphate form, which we've seen before. The triphosphate alpha, beta, gamma phosphates, all connected on carbon number 5. All right, so this molecule here, adenosine triphosphate, can be converted into adenosine diphosphate, ADP, by removing that gamma phosphate. Now, we put this into thermodynamics concepts. What's going to happen is this phosphate is going to break from this other phosphate. The gamma phosphate is going to break away from the beta phosphate. And when it does that, there's a bond that breaks, the bond right where the cursor is right there. When that bond breaks, the bond is going to release energy, free energy. Therefore, this reaction is exergonic. When it does that, it releases free energy. Now, the phosphate can't just disappear. The phosphate ends up just sort of free on its own, and it can be transferred to something else. It can be released just as free energy, as free phosphate floating around, inorganic phosphate in the serum or whatever it happens to be. But the point is that this reaction releases energy, therefore it's exergonic. Okay, now what's a delta G? And is it spontaneous or non-spontaneous? Okay, going back to what we talked about earlier, the delta G has to be negative because it's exergonic, and it is spontaneous. It's a spontaneous reaction, and that means this: adenosine triphosphate will become adenosine diphosphate on its own, right? So why is this so important? Why is this the most important? It's often called the most important reaction in all of biochemistry. Well, the reason it's most important is because this is the step that you usually use, that living systems usually use, when they transfer chemical potential energy into some other form of energy. Okay, like moving an ion, throwing a ball, talking, walking, pumping your blood in your heart. All of those kinetic events are driven by this biochemical reaction of adenosine triphosphate ATP becoming ADP. And that energy that's being released there is therefore the connection point between chemical potential energy and some sort of kinetic energy in your system. And as with all biochemical reactions, we can also go the other way, where we take adenosine diphosphate, add a phosphate to it from some other source, and make adenosine triphosphate. And again, we're just adding a gamma phosphate onto the beta. And again, that bond right there has energy in it. So in order to do this, we need to have an outside energy source that will supply the energy to be able to form that bond between the beta and the gamma phosphates. So that makes this reaction endergonic, and therefore the delta G is positive, and therefore it is not spontaneous. There has to be some energy source out here to actually supply that energy and that oomph to actually put that phosphate onto the ATP. So here's the cycle. We can start with ATP, and we can break it down into ADP and phosphate, and then we can do the other. We can take ADP and a phosphate and make it into ATP. Now, the energy that's released or used to do that is, like I said, not a huge amount. It's fairly sizable for the size of the molecule, but in other molecules, like I said, NADH has a lot more energy in it that can be metabolically available, and certainly glucose has 100 times more energy. But the amount of energy that is released is a number I want you to know. If you take 1 mole of ATP, now remember at this point in your career, you're not allowed to forget anything anymore. You know what a mole is. If you don't know what a mole is, go look it up, make sure you understand it. A mole is simply a large number, and I'm talking about taking a large number of ATP. The number happens to be 6.022 times 10 to the 23. Take that many ATP and break them down, all of them, into ADP and free phosphate. If you do that under standard conditions, which basically are the conditions of your body, you will get a delta G of minus 7.3 kilocalories. All right, that means that the energy that's released is 7.3 kilocalories. All right, now notice this is not going to minus here, and that's because this is the whole cycle. What this says is that if we go from ATP to ADP, you know the delta G is negative, and therefore this is minus 7.3 kilocalories per mole. But if I want to make a mole of ATP, I want to make 6.022 times 10 to the 23 of these ATPs, I need a mole of ADP and a mole of phosphate and this much energy, 7.3 kilocalories. The exact same amount of energy that I get released is the amount of energy I need to make this mole of ATP. So that then is the cycle and requires that much energy and releases that much energy when it goes through it. Now here's the interesting thing. If you look inside your cells, every single one of your cells on average has about 2 billion ATP molecules in it. Only 2 billion. If you look at the rate at which the ATP is being burned into ADP and phosphate, and I say burned because this is an oxidation reaction, we'll talk about that later, but whenever you take ATP and make it into ADP, if you look at the rate at which the cells do that, you'll measure about 100 million of these ATP per second. 100 million, and you've got 2 billion in your cells. Think about that for a minute. 2 billion, 100 million. How many seconds does your cell have to live? How many seconds before it runs out of ATP? I can tell you right now, if it runs out of ATP, it's going to die. The reason it's going to die, if nothing else, is because it's going to lose control over the sodium and potassium concentrations that we talked about in the last lecture. If it loses control, remember, the cell swells and bursts. So if it runs out of ATP, the cell's going to die. It's burning ATP at 100 million per second, and there's 2 billion in the cell itself. So how long before that cell runs out of ATP? If it doesn't do anything, take 2 billion divided by 100 million, you get 20 seconds. So your cell, every single cell in your body right now is about 20 seconds away from death when it's at rest. If it's active, it's even worse, though. It's using ATP at a much higher rate. So 20 seconds away, you're going to run out of ATP. So what does that mean? Well, it means you've got to have something that is regenerating that ATP at the same rate. It has to be the same rate. If it's faster than the rate at which you're burning it, then the amount of ATP in your cells is going to increase, and it's not. It's not doing that in reality. And if it's slower than that, then you're going to be burning ATP faster than you're regenerating it, and so you run out of ATP, but slower. So the point is that your cells have to have something that is taking this ADP and phosphate and making ATP out of it at a rate of 100 million per second. 100 million per second at every single one of your cells. What is that? What is doing that? Well, remember, whatever's doing that requires energy, because this ADP and phosphate to ATP is endergonic. There has to be an energy source. So what's the energy source? Where are you getting the energy from? Ladies and gentlemen, this is why you eat. This is precisely why you have a stomach and a small intestine and a circulatory system. The whole purpose of eating is to ingest chemical potential energy that then gets fed primarily into this system to regenerate the ATP that you're currently using. Right? So that's what this arrow represents. The energy here, you should cross that out and write food. That's what that is. That's food. Now, it says here exergonic cellular respiration. But this reaction, ADP plus phosphate to ATP, is endergonic. So why does it say exergonic on the endergonic side? Well, look at it carefully. You can see why. This is endergonic. Therefore, something has to be giving this system energy. What's giving the system energy must be exergonic. And they're calling it cellular respiration. And that's what we're going to be studying for the remainder of the course. Cell respiration includes things like glycolysis, the Krebs cycle, things like this. So this is an exergonic process that produces energy. It doesn't really produce it, it just transduces it, puts it into a form that you can then use to regenerate that ATP. But then the ATP, why are you burning it so fast? Why are you using it up so much? Well, again, every time you change your state, every time you move, every time you breathe, every time you pump blood, every time you move ions across a membrane, every time you have a thought, you're using ATP. ATP is being used to drive that chemical change into a mechanical or some other sort of electrochemical change. So this ATP then is being used, the energy is being used then for some sort of endergonic process. Okay, now remember, this is exergonic. ATP to ADP is exergonic. The energy is being released. The energy has been being used for endergonic processes. Okay, now we see two examples of this then. Energy from exergonic reactions are being used to drive an endergonic one, here and here. Right? That's a pattern we're going to see over and over again. So that whole process really is what metabolism is all about. It's changing energy from one form to another. Some exergonic reaction occurs, which drives an endergonic reaction. You want to get up and walk? Objects don't just move on their own. A rock will not get up and walk across the room, but you can. And the reason you can is because you take a bunch of ATP, release that energy from the exergonic reaction of making it into ADP, and use that energy for the endergonic reaction of moving your body from one place to another. Okay, so here's a summary. If we're looking at any kind of a closed system, now take a moment to define in your mind what a closed system is. Make sure you know what that is. If not, go back to the earlier part of the lecture and take a look at it. What we're talking about now, reaction involving transformation of energy in a closed system, meaning that the system changes state in some way. The first law says that within that system and in that change, the total amount of energy is constant. The enthalpy, therefore, H, is constant. The second law says that the entropy, S, cannot decrease. That's another way of saying that the amount of energy in the system that's available to do work within that system is not increasing. So the entropy cannot decrease. There's another way of saying that second law, and that is that when you have a closed system, the delta G of every reaction has to be less than or equal to 0. It can't be greater than 0. Okay? All right, now what that means is, again, remember how we calculated or how we measured entropy. Entropy is the number of degrees of freedom of motion within the system. So entropy, the number of degrees of freedom of motion, must always increase. At least it can't decrease. So in other words, I can't, without an outside energy source, a closed system could not take 3 pens and put them together spontaneously into one object like I showed before. Okay? But now, I want you to consider, though, those statements in this context. What you're looking at here is a slice of tissue through the root of a plant. And this tissue right here, this red sort of ring that goes around, is called the peristele, P-E-R-I-S-T-E-L-E, the peristele, which means literally around the star. And you see this red cross right here, that's the star. The red tissue here in the inside of this circle is the xylem, X-Y-L-E-M, and these little 4 patches of green tissue are phloem. Okay, now I'm not going to get into the details of what these things are doing. You'll do that in Bio 182, but the xylem, for the short story, is basically taking water and nutrients from the roots up to the shoot and then to the leaves, and the phloem is distributing the stuff that the plant makes through photosynthesis throughout the body of the plant. And all of this tissue outside of the peristele, all this stuff with these big huge cells with these sort of purple granules in them, each one of these purple granules is a starch grain. And that's how the plant stores its energy. You store it as fat, as adipose tissue. This is the equivalent of adipose tissue in a plant, but it stores as carbohydrate, not as lipid. Okay, but this then is a pretty organized structure, if you think about it, right? You got this circle, which is there, you got this star, you got the phloem all packaged up, and you got all this tissue out here. By the way, that tissue is called parenchyma. If you're looking at all of this tissue, you have to realize this came from carbon dioxide and water. Carbon dioxide from the air, water from the ground. So all those carbon dioxide molecules, all those water H2O molecules were taken in by the plant, rearranged into this. Okay, now let's think about what happened to entropy. Okay, which has more degrees of freedom of motion, therefore which has more entropy? All the carbon dioxide and water separated, or all of that same carbon dioxide and water put into this structure? Right? It's pretty easy to see that the entropy, the total number of degrees of freedom, is much higher when the carbon dioxide and water are free than when they are put like this. Okay, therefore, what is the plant doing? The plant is taking something with a bunch of entropy and making it into something with less entropy. Okay? Now, this just says right here, though, the entropy can't do that. Go from high entropy to low entropy, it can't do that. S cannot decrease. In other words, the Gibbs free energy has to always decrease. But here, the Gibbs free energy had to be positive. Why? Well, the amount of ordering had to increase, and that means entropy is decreasing. Gibbs free energy is doing the opposite. It must be increasing. Okay, so how do we figure this out? People have made the same argument as to why it is that evolution isn't true. Evolution can't violate this second law of thermodynamics. Well, this is a much worse problem than that, because this is something that is very obviously violating the second law. It's violating it. Well, it's not really, because what's the key phrase? Closed system. This plant is not a closed system. That's why it can do this. Open systems, like evolutionary systems, can have a delta G that's either positive or negative, can have entropy that's either positive or negative. In fact, in an open system, the enthalpy, the total energy, can be different. It can increase and decrease. You can't destroy the energy and you can't create it, but you can bring it in from the outside or you can dump it to the outside. So in this case, an open system, these laws don't apply. And a living system like this plant is always an open system. But that tells us something actually very deep. All living systems must be open. It's impossible to have a living system that's closed because there's no amount of energy that can be brought into that system or released from that system if it's closed. That's the definition of a closed system. So all living things must be open. That also means this: all living things must do the equivalent of eat. There has to be some source of energy coming into that system, and not only that, but there has to be some way to dump the entropy out. Okay? So what do? Well, you gain free energy by eating, but then you produce a bunch of entropy. What do you do with that entropy? Well, it is not released in any grotesque way. It's released as heat. Your body produces heat, and that's the entropy that you're dumping into the system. And if you don't produce that heat, if you don't release the heat, then your body would die. So you have to have those two things. You have to have a source of energy coming in, and you have to have a source of entropy to be dumped out.